Welcome to today's class on functional analysis. Today we discuss two-norm theorem. This is theorem 11.3 in your text. So if we state the theorem 11.3, let X be a Banach space in the norm then a norm dash on the linear space X is equivalent to the norm if and only if X is also a Banach space in the norm dash, and the norm dash is comparable to the norm norm. So now we prove this theorem. Proof: let norm dash be equivalent to norm. That is, each of the norms, norm and norm dash, is stronger than the other. Therefore, norm and norm dash are comparable. That is, norm dash is comparable to the norm. Now since X is complete in the norm, by 6.3a, X is complete in the norm dash. That is, X is a Banach space in the norm dash, and norm dash is comparable to the norm. So this proves the first part. Now we prove the converse. Conversely, assume that X is a Banach space in the norm dash, and the norm dash is comparable to the norm. So without loss of generality, assume that norm is stronger than norm dash. Therefore, there exists alpha positive such that a norm dash of x less than or equal to alpha times norm of x for all x in x. This is by 5.7. So we let y denote the linear space x with the norm dash, and consider the identity map I from x to y. Then I is bijective, linear and continuous. Then I is bijective, linear and continuous. Therefore, by bounded inverse theorem, I inverse from y to x is also continuous. That is, norm of I inverse of x is less than or equal to gamma times norm dash of x. So this implies 1 by gamma, I inverse of x is x, 1 by gamma times norm of x is less than or equal to norm dash of x. And this is less than or equal to alpha times norm x. So let beta equal to 1 by gamma. So this implies beta into norm of x less than or equal to norm dash of x. This is less than or equal to alpha times norm x for all x in x. Therefore, the norm and norm dash are equivalent. So this proves the two norm theorem. So the above result can be restated as follows. May I write it as a note. The above result shows that two comparable complete norms on a linear space are equivalent. We can write some remarks based on the two norm theorem. Let X be a Banach space in the norm. So the following question arises. Question number 1. Is there a norm dash on X which is comparable to the norm but in which X is not complete? The answer to this question is yes, since if you let x is equal to C01 and subnorm of x to be supremum modulus of x of t such that 0 less than or equal to t less than or equal to 1, and 1 norm of x to be integral 0 to 1 modulus of x of t dt for x in x, then x is complete in the norm subnorm, and you know that 1 norm of x less than or equal to subnorm of x for all x in x, but x is not complete in the norm on norm. That is, there exists norm one norm on C01 which is comparable to subnorm, but X is not Banach in one norm. So the answer to the first question is yes. Now we can pose the second question. So the question number 2, is there a norm dash on X in which X is complete but which is not comparable to the norm? So answer to the question is also yes, since we let Y be an infinite dimensional Banach space over K and F be a discontinuous linear functional on Y. Such a linear functional exists by 6.1. So let X equal to set of all ordered pairs Y K such that Y belongs to Y and K belongs to K. And for X in X, you define two norms, that is X is equal to ordered pair YK in X. Let norm of X to be norm Y plus modulus of K and norm dash of X to be norm Y plus modulus of f of Y minus K. Then norm and norm dash are complete norms on X. However, they are not comparable. We are going to show that they are not comparable since f is a discontinuous linear functional. There is a sequence yn in Y such that norm of yn is less than or equal to 1 and modulus of f of yn tends to infinity as n tends to infinity. Then norm of yn0, by definition this is norm yn plus modulus of 0. So this is norm yn. This is less than or equal to 1. And norm dash of yn0. This is by definition norm of yn plus modulus of f of yn minus k here is 0. So this is norm yn plus modulus of f of yn. So this tends to infinity as n tends to infinity. While norm of yn f of yn, by definition this is a norm yn plus modulus of f of yn, and this tends to infinity as n tends to infinity, and norm dash of yn f of yn, this is equal to norm yn plus modulus of f of yn minus f of yn. So this is equal to norm yn. This is less than or equal to 1. Therefore, X is complete in norm and norm dash, but norm dash is not comparable with norm. That's all for today. Have a nice day.